Thanks very much. It's a great pleasure to be here. I was starting my second week, and so I had a very interesting, nice, relaxed environment, and also very good to hear, get a chance to interact with people, outside of my usual condensed matter milieu, and so learn about what's interesting to other people in kind of peripherally related things to what I mostly think about. So I was asked to give an overview to nonlinear and non-equilibrium, nonlinear optics and nonlinear non-equilibrium effects in solids. And this is a huge area. I couldn't hope to do it justice in a whole week of lectures. And so I can't come anywhere close to it in an hour. I'm gonna give a kind of a personalized perspective on some things which I think are interesting. They're interesting to me. They're also, I think, should be interesting to kind of a larger group of people, particularly a group of people who are interested in strongly correlated metals. And so I'll be telling you mostly about, I'll get there eventually, but where I will eventually get to is telling you about various kinds of experiments that my group and some other groups are doing on nonlinear effects using low frequency terahertz radiation to look at correlated metals. So that's eventually where we're going. And I'll get there in a kind of roundabout way, and we'll talk about conventional optics and on our way to learning about nonlinear optics. At the outset, let me say that it's not necessarily obvious that you would want to do nonlinear optics and strongly correlated to understand something about strongly correlated materials, right? So if strongly correlated material is it's quote unquote impossible to understand, and generally non-equilibrium physics has the same difficulty, kind of presents real difficulties in trying to come up with some kind of tractable understanding of it as well. And so impossible to understand times impossible to understand, impossible squared is not necessarily an important and obvious route towards to learning about the physics of things. But I hope to make a case to you that through a kind of a new class of experiments that are nonlinear, but specifically target low frequencies, that we can get insight into particularly quantum materials in general, but in particular correlated electron systems that give us new information in a controlled way and information that we can't get in other fashion. Okay, so before I do that, let me thank various people that have made the work possible. So this is my group from some years ago now. Hélène is not here today, but I in particular wanted to point out Hélène Rafi, who I've kind of had on and off collaborations with for many years, but the various bits of data are still unpublished, but we're coming to the end. And I'll show you a little bit today about a very, very nice study using her films, but I got to meet her in person for the first time this last week. Let me point out the various postdocs, Kota Katsumi, who's now an assistant professor at NYU, David Barbalas, a student with me, Deepanjan Chaudhuri, who was a student with me, then a postdoc in Illinois with Peter Abamonte, who was here last week and now will be an assistant professor at the University of Notre Dame, Willie Young, a current student, and Fahad Mahamud, who started this work as a postdoc with me, who's now an associate professor at the University of Illinois. And thanks a lot to various sample growers over the years, theoretical collaborators, and the people who supported this. We start in the beginning. In fact, you'll see this slide in a few occasions here. So when we're thinking about the response of materials to radiation, we usually think of it in this kind of perturbative scheme. And in the conversations I had this week, one thing I learned is that I come away with a perspective that different communities have different ways of thinking about these various different proportionalities here that I call response functions, but they can be written variously as different multi-point correlation functions. How many point correlation functions, whether it's a 2-point or a 3-point, depends not necessarily on what term this is, but what your convention is for counting points. And so I think that's one important thing to understand, is that very often the language that we use in different subfields of physics can be very different about different things. But this is going to be our general starting point. And in fact, I changed the title of my 30-minute talk later this afternoon, where I'm mostly actually going to think about this guy here, about linear response. Okay, and because why? Well, linear response is the simplest thing that we have, and it's the most powerful. But of course, it's not the only thing. So the talk now is mostly about kind of trying to lay the groundwork for a new way of doing spectroscopy, for correlated systems. But I'm going to kind of go back in the talk this afternoon and talk just about what we learned in linear response. And we like linear response because it's simple and powerful, but of course, it's not the only thing. Very often when we're thinking about the response of material, its response to kind of higher order, forms of the perturbing force, perturbing fields, we enter in this particular fashion. So some kind of perturbative scheme, right? And there can be various, these are tensor forms, and so there are various symmetry constraints on them. We'll talk about that in a moment. But famously, for instance, the chi2 susceptibility is only allowed with this particular form when a system breaks inertial symmetry. So I'll mention that again in a different context. But these things, in addition to giving us dynamic information about materials, can be very important probes of symmetry. One of the things, of course, we're after, and is something that's a big focus of this meeting, is the linear resistivity in the cuprates, sometimes so-called linear Planckian resistivity in the cuprates. And so this is a plot we've seen before. So this is resistivity over up to a really large temperature scale, right? Well over 1,000 degrees. This is almost the melting temperature of lanthanum strontium copper oxide. And it's kind of implicit in this when you see resistivity, plotted resistivity, but what people really mean, or what they're thinking of, is the scattering rate. Because there's a proportionality in the Drude model between the scattering rate and the resistivity. But one thing to point out, that in an optical conductivity experiment, right, which is the first term in that expansion, we can measure this quantity just directly, basically in absence of any interpretation, and we can measure its magnitude. Right? So it is just, this is the optical conductivity of lanthanum strontium copper oxide as a function of frequency. Red is warm, blue is cold as we cool down. And the rate that current dissipates in the system is literally given by the width of this peak, right? There's no interpretation in that. That's just what it means, right? That there are current correlations in the system which decay exponentially. And if the conductivity is a Lorentzian, this means that the width of that peak, again, absence of any interpretation, is the rate that current dissipates. That just comes from basic definitions of response functions, right? So I only mention this because I think it's important, particularly when talking to community people who are really thinking about kind of fundamentals about what do the responses actually mean. But I also mention it because sometimes people will say things like, well, if it means if you're fitting with something that can be fitted with a Drude model, that means it's not a Fermi liquid. Well, it's just not true. What it means is that it has, if it fits to a Lorentzian, it means it has time correlations which are exponential in time. So we can take that width and we can plot it as a function of temperature. And here it's only plotted over a reasonably small temperature region, right? This goes all the way out to well over 1,000 Kelvin. This is only up to 100 Kelvin, but linear in temperature with a coefficient close to 1 with a very small offset, right? So this is what we need. We'll come back to this. So this is something to be understood. And one of the ways that we hope to understand it is through these nonlinear response functions. As a way of advertisement, but if you're interested in these topics, also for people who are online, I have for many years kind of kept this, if you will, living document, electrodynamics of correlated electron systems, which I hope to never publish. It will just sits on the archive. And, every few years when I have some things to put in it, I update it. And I think it's, again, a living document for what is interesting to me. When I go back and look at it now, I started this in 2008. And it's interesting, what's interesting to you at one time versus what's interesting at another time, and things wax and wane in their interest. But anyway, if you're interested in these topics, take a look at this document here, which you can find easily by Googling me and finding it on the archive. Oh yeah, oh right. So, I think with anything, the best teaching is very often where you get a strong feeling for what's important from the teacher or the lecturer. And I still like what I wrote back in 2008. This short review and lecture notes attempts to lay out a brief summary of the formalism, techniques, and analysis used for optical spectroscopies of correlated electron systems. They are idiosyncratic, occasionally opinionated, and considering the breadth of the subject, incredibly brief. And so that's, of course, also going to be with the lecture team. Okay, as a broad audience, let's just kind of set the scale for what we're talking about. That's the electromagnetic spectrum.
Can I ask you a question?
Sure.
So you showed that new, very interesting plot of the cuprates where you get from optical spectroscopy directly a time which is linear. I'm curious, what is this? Is there something similar for T-linear phonon electron scattering, T5 electron phonon scattering, and T-square electron scattering in conventional materials?
Can you measure this? You mean to see?
Yes. Is there something like that? Since you mentioned this review of yours,
Yeah.
so coup plates are strange methods.
Sure.
So even if we understand the agreement, we still don't understand.
So there are lots of work on this and people looking for T-squared scattering in nominal Fermi liquids. There's a few caveats that have to be given. So what I said was, you're directly measuring the rate of current relaxation, right, from the definitions, right? So there's no debate about it. That's just what it means. But it's current relaxation. Very often what we want to think about is the relaxation rates that come from some microscopic process. And maybe we have in mind, scattering from one particular Fermi surface sheet or something like that. So it's a different matter altogether if you want to calculate the rate of current dissipation to the rate that, say, individual quasi-particles might, particularly if you have like a multi-band system.
But my question was more experimental.
Yeah, okay. So experimentally, the answer is yes. So people in strontium ruthenate have seen omega squared scattering. I don't know of examples where people have seen, like, say, T to the fifth scattering from electron coupling off of acoustic phonons. But that would be an interesting.
That needs to go to very low temperature. Maybe you need high resolution.
Yeah.
Okay, thank you. That's
but if that answers the question.
But I thought, for instance, the T-squared resistivity was because here you mentioned strontium ruthenate, which is already a more complicated metal, but I thought, like, in simple metals, observing T-squared resistivity was actually hard.
That's right. Yeah. So we don't have very good examples of where it would be a Fermi liquid, but with really large scattering, which dominates. So,
well, dilute metals,
So maybe dilute metals, but as you know better than any of us, that presents its own challenges, both in the interpretation is, it's hard to say that those are canonical T-squared Fermi liquid scatters. I mean, maybe they are, but certainly if our interpretation of them is dilute metals have that, then we have to understand some other things first. So there are reports of seeing T-squared, or say, let me put it differently, omega squared scattering, the scattering rate, in gold, silver, copper, but I'm not sure that I really believe all of those. There's a bunch of technical issues with that. It's hard to see, I agree.
It's interesting.
Okay, so about energy scales here. So 1 Kelvin would be about right there. 100 Kelvin about right there. 1,000 Kelvin would be right there. One of the things, since this is at least partially an overview, one of the things you find is a challenge if you're not from the world of optics and you're coming into this field is just the blizzard of different units that are used for trying to understand one thing versus the other. People will talk about millieV. I like terahertz. Inverse wave numbers. I mean, what the heck is that? That's something that very few people, but still infrared spectroscopists talk about. Degrees Kelvin is maybe a nice universal units. This provides some kind of correspondence between, and then there's of course inverse of all that wavelengths. I usually tell people to remember that up to factors of pi over e, 200 gigahertz is 10 Kelvin, is 1 millieV, is 10 wave numbers.
I get particularly frustrated.
What's that?
I get particularly frustrated between the uses of omega versus nu, and the 2 pi's that
omegas and 2 pi's. Yeah. This is also
including in your papers.
Yeah. I can only just apologize. I can't explain.
It's fine.
Yeah. Okay, good. So back to what we had there, right? And so I showed you this slide before. When we're thinking about the response of systems, interesting, complicated materials to electromagnetic radiation, we like linear response, right? Because it's simple and it's powerful. We can do a lot with linear response, but all physical systems have nonlinearities. Very often the nonlinearity is a source of complication, but the nonlinearities can also be a source of interesting phenomena. Right? And they can be an interesting source of information. If we're going to investigate systems and try to look at these higher order terms in a complicated physical system, we better have a good reason for doing so, right? We should have a kind of a physics forward approach where there's really going to be unique information we can get from doing it, because things get a lot more complicated very quickly. Okay, about linear response, let me just kind of skip through this, but one of the reasons we like linear response, there's kind of a nice formalism. This is discussed all in these lecture notes that if you're interested, things like the Kramers-Kronig relations, where there's kind of a straightforward way of applying them. If we know the real part of the complex response function for all frequencies, we can find the imaginary part for any frequency, vice versa for sigma 2. We know sigma 2, the imaginary part for all frequencies, we can find the real part for any frequency. Very often, what we do know, and particularly that's the case in time domain terahertz, is we actually know the full complex response, but in a limited frequency range. So we know the real and imaginary parts in some frequency range, and we want to learn about something which is outside the frequency range, and that's something which is possible to us also with Kramers-Kronig. Again, the linear response functions are the simplest we have, and they're powerful, and one of the reasons they're powerful are for these kinds of reasons. I'll talk about this a little bit more in my talk later today. Oh, there's optical conductivity, just to give you, like, again, a simple case of something. That's the response functions are complex quantities. So that's the real part, sigma 1. That's the imaginary part, sigma 2. This is really, the dashed line is just the Lorentzian. The half width of this is literally, as I said before, just the rate that current dissipates. So that's its definition. There's no debate about what that means. It just comes from definitions. And then there's an imaginary part, which is Kramers-Kronig consistent with the real part. Okay, back to that. Let me talk about the nonlinearities. Right? So optical nonlinearity is, of course, an old subject. As I mentioned, all physical systems have nonlinearities, and they're often a source of complication. We very often would like to look at a system at low energies, low frequencies, low excitation amplitudes, because we want to work in a regime where linear response is applicable. As we drive the system harder, we can get nonlinearities, and those nonlinearities are often a source of complication, but they can be an interesting source of phenomena, and they can also be a source of information. Right? So there are different names for these, and again, optical nonlinearity is an old subject, and so there's a lot here to learn about. But these some of the different processes go by names like second harmonic generation. And here, microscopically, you can think 2 photons come in, and 1 photon comes out with 2 times the frequency of the photons that were going in. There's a third harmonic generation, which is a version of this. 3 photons come in, 1 goes out. And then we can also understand, this is kind of considering a system interacting with a field which is modulating at omega, another field which is modulating at omega. But in a case like this, we can imagine that the system is modulating with omega 1 and then interacting with a photon, which is actually its complex conjugate. So it's interacting with a photon, which is e to the minus I omega. And so then you get things like difference frequency generation, where you have positive frequencies and negative frequencies. There's a chi3 version of that, which is called four-way mixing. And when we're thinking about two-dimensional spectroscopy, 2D coherent spectroscopy, where the 2D is 2 frequency dimensions, and how that all works, I'll tell you about it in a moment, this is actually the most important process. Right, optical nonlinearity, as I mentioned, is an old subject. Shortly after the discovery, the first generation of the Ruby laser, there was the first demonstration of optical nonlinearity in a material system, and this was a PRL, now famous, 1961, which is second harmonic generation coming from quartz. And you can read here, it's written, the arrow at 3,472 angstroms, right there, indicates a small but dense image produced by the second harmonic. So that's the first harmonic, that big spot. There, it says, indicates a small but dense image produced by the second harmonic, but there's nothing there. So famously, the copy editor thought this was a speck of dust. And this seminal result in optics and nonlinear physics was the speck of dust, as they thought, was taken out of the image and removed. It was later corrected, and you can find the actual image, which was put as an erratum in the next issue of Physical Review Letters at that time. Okay. That's Chi2. That was a Chi2. But Chi2 is also, I'm not going to talk so much about Chi2 today, but Chi2 is an important response function. And one of the important things is that at the level of electric dipole coupling to the system, Chi2 is only possible when you break inversion symmetry. There are higher order couplings, say gradient couplings, that can exist, which can give you, which is effectively a Chi2, but these are very weak. Generally, if you see a Chi2, that means the system has broken inversion symmetry. And if we're thinking about, this has been the case in materials oxides, where there can be oxides have oxygen, there can be subtle structural distortions, the octahedra. The usual way we look for structure is through X-ray diffraction, but X-ray diffraction is notoriously very insensitive to the positions of oxygens. So this sees distortions of oxygens just fine. And so we have, I'm sorry, I'm kind of skipping ahead. The Chi2 is sensitive to broken symmetry. And in this particular study, what we did some years ago, primarily coming out of Dave Shea's group, but I was a little bit involved with this, where we showed that the pseudo-gap regime of the cuprates was formed by a line where there was a sharp onset in the Chi2 signal that came up, which there's a long-term debate about the pseudogap with cuprates. Is it, there's kind of this low energy gapping phenomena that nobody really quite understands. Is it a crossover phenomena, or is it a real line of broken symmetry states? Well, what this shows is that it's a real line of broken symmetry states, because this is zero, the signal is essentially zero above and finite below, and it's forming there, that onset is right along a line where spectroscopic evidence indicates that the pseudogap shows up.
Right. Does inversion here means parity? Is that what you mean?
Inversion essentially means parity. Yeah. So materials can break inversion. We say break inversion, or crystal structures can be non-centrosymmetric. Right. So there's a few versions of this, but they all, as far as this is concerned, are the same. And so if R to minus R is not a symmetry of the system, as it's not in a chiral system, but also just in a ferroelectric material, or also not centrosymmetric, they can generate Chi2 sources of radiation.
So you're saying that this 3-point susceptibility, or Chi2, can only appear if you have parity breaking in the system?
At the level of dipole coupling to the system, yeah. So you can have higher order like gradient couplings. So you can have a coupling which is like E grad E. But this is very small typically, because it's usually suppressed by the size of the dipole, which is microscopic, unit cell at best, divided by the wavelength. So that's a small number typically. But at the level of the dipole approximation, that's right.
Yeah. Because generally how I think about susceptibility, these are static susceptibility, right? Chi2. So I typically think of it as how charge density responds to chemical potential. And so this will be that density 2-point function will give you Chi1.
Yeah, I'd have to think about what that means translated into my language, but I would normally think of it as you said compressibility. I mean, I think of compressibility as a linear order response. Right?
Yeah, I mean, susceptibility, right? So I would think of Chi as static susceptibility.
Mm-hmm. Yeah. Let's talk about that. The other thing that I wanted to mention, they got out of order here, is that one thing we've known this focus of this meeting is mostly about correlated systems and less about topological ones, but the topological materials, for instance, were materials where strong Berry curvature effects and quantum geometric effects are large, have been a hot topic in condensed matter physics for the last 15 or 20 years. And one of the things that we know now is that for systems which break the break inversion symmetry, that the Chi2 nonlinear response is in particular very sensitive to Berry curvature. And so, for instance, a class of materials that we call vial semimetals are known to have the largest Chi2 response of any material that anybody has ever measured. So another thing that you'll see later today with an exceptional response of cuprates in terms of their nonlinearity. So, a lot of, perhaps unsurprisingly, a lot of the materials that we find interesting in condensed matter physics also have exceptional properties that may be interesting for applications as well. Okay, so this is an example. Okay, so now let me tell you about what we're working on and what other groups are working on in this relatively new technique of so-called terahertz 2D coherent spectroscopy, so 2D CS. And here the 2D is two frequency directions. So I'll tell you what this means and how it all works. It's it's kind of a bit of a specialized topic, but I think it's one which really cuts it to the heart of what we're interested in the world of correlated metals. So again, 2D refers to frequency directions. So it's a way now of thinking of kind of a more generalized spectrum. If a normal spectrum, frequency, intensity, is a one-dimensional spectrum, now we can think of a spectrum as kind of a possibly higher dimensional object where it has frequency responses in multiple directions because there are multiple drive frequencies. So let's start with a very simple example, okay? And I want to imagine doing an experiment with two pulses, and we're going to call them pulse A and pulse B. And we're going to imagine driving a system which is some weakly nonlinear oscillators. So you can imagine them like charged pendula, and I can drive them with electric fields A and B. And I'm going to do this experiment with A and B together. And then I'm going to do an experiment just with A and then just with B, and then I'm going to look at the difference. And so if the system was purely harmonic, described by linear response, I would get 0. And so that's what happened. That's kind of the definition of linear response. It doesn't matter if you drive it twice as hard, you get twice the output. But if I have some residual when I form this difference here, that's going to tell me something about the nonlinear response. Okay? So now let me imagine again, I'm going to drive these two weakly nonlinear pendula, and I'm going to plot their spectral response out of the page here. And so a feature of a nonlinear oscillator is that if I drive it at some frequency, and I drive it hard at that frequency, its oscillation frequency shifts. Okay? So what I can imagine is if I pump it with one frequency, let's call it A, and drive it with a probe frequency at some later time, I can kind of tell when I'm probing it that I pumped it at the right frequency. But if I have probing it at some later time and I pumped it at the wrong frequency, I don't necessarily see anything. Okay, so that's the basic idea. Now, very roughly speaking, the projection of the probe frequency on the projection of these kind of two spectral responses on the probe frequency axis, that's the linear response. Okay. Now, imagine a situation where let's say I have these two oscillators, but now I'm going to go and I'm going to couple them together. Now, what happens in the linear response? Again, this projection here is roughly the linear response. If I have two coupled oscillators, if I have two oscillators and I couple them, what happens? Well, they shift, they broaden, perhaps they become asymmetric. If I have a good enough theory, I can make some story about what that coupling might be, but I seldom have good enough theory. But in the nonlinear response, it's not a matter of having good enough theory. I just get new peaks where I didn't have them before, right? So it's literally as simple as just I can go in and I can shake the green guy and I can make the red guy move. Right? So you get the essential point, right? So one of the things the technique is going to be very good at is if I have well-defined excitations, is looking at the coupling between them, weak couplings in these nonlinear systems. Another thing you can imagine doing is imagine that, for instance, maybe I have these oscillators and they're all rather long-lived, but they're they congest the spectrum in such a way that maybe the linear response is just this big blob. It could be made up of many long-lived modes, but I can't see them spectroscopically because they're all just overlapping on top of each other. But they provoke this, in the nonlinear response, this ridge in frequency space, and I could imagine doing a cut in the anti-diagonal direction in this regard, resolving the lifetime of these modes. This analogy is something we're going to come back to in a little bit. Okay, so we didn't invent this. I mean, it wasn't invented by physicists. Mostly invented, the ideas were invented in the context of nuclear magnetic resonance, where nuclear magnetic resonance you use to generally radio frequencies, and you excite nuclei. So 2 Nobel Prizes have been won for doing 2-dimensional nuclear magnetic resonance, and it's been used for working out the structures of large biomolecules. This is a structure here for codeine, right? So anesthetic. And here are these kind of projections, if you will. And the way the structure of codeine is worked out here is you got these guys along the diagonal. And so if you get cross peaks, you kind of have some suspicion about what makes that excitation and what makes that excitation. And if you get a cross peak, that means those 2 nuclei are close to each other. And if you don't get a cross peak, let me find one right there between those 2 strong guys, that means those nuclei are far from each other. So this has been used a lot in at much higher frequency ranges, looking at vibrations and molecules. So imagine you have a protein, and the protein undergoes some kind of conformational change and folds. So I have this little thing that vibrates here, and that little thing that vibrates there, and then it folds, and these 2 things come close to each other. As a function of time, you can see these cross peaks rise up. Right? So that gives you another example for the kinds of things that are happening. As I said, 2 Nobel Prizes have been done for that. What has happened is, so these are all either radio frequencies, very low frequencies, too low for us really to worry about what happens with electrons there, or in the half eV to eV range, talking about high frequency molecular vibrations. What's happened in recent years is that we can take this technique and apply it in the terahertz range. So what I told you about in the beginning, I showed you the spectrum. And so a few milli-eV corresponds to 1 terahertz. A few milli-eV corresponds to tens of Kelvin. And so if I'm interested in phenomena that is perhaps exhibited at the tens of Kelvin stage, this means frequencies in the order of terahertz are important, and we can use it to probe various interesting low energy phenomena. Let me say also, Peter Almonte gave a talk last week where he was advocating for gentle probes of solids. And I really appreciate this point. I think it's correct. We don't, when we have some complicated many-body system, the last thing we want to do is really jam it hard and drive it very far from equilibrium, because perhaps whatever hope we had of understanding what was going on will go away. What I like about this technique, it's a nonlinear technique, and by its very nature, then it's non-equilibrium. but we don't push the system very hard. So it's kind of, if you will, the next correction to the gentle techniques. It's low frequencies. And so very often the kinds of nonlinear spectroscopies that people do are using high frequency lasers. So they use like a 1.5 EV laser. If you take 1.5 EV and you correspond it to temperature units, that's 15,000 degrees. Right? So that's a huge energy scale for, if you think about cooperative phenomena, it's called solids. We're using photons, which are milli EV, which is tens of kelvin. This is what one of these kind of setups looks like. You have an ultra-fast laser, which produces some pulses, goes around the table. I won't tell you about all the business, what this does, but the kind of the important part is right here and there, where we create these approximately picosecond long pulses of radiation, and we can measure them, delay them past each other, put them through the sample in that particular fashion. That's another version of what data looks like. Remember what I had said is I want to do an experiment with A by itself, B by itself, A and B together, and then I look at the difference. And so that difference is the nonlinear response there, again, kind of by definition. Okay. Are there any questions at this point? I'm going to show a few other things, but yeah.
Yeah, is there a particular reason for the shape of this profile? And would you like it to be different if you could?
Yeah, so that profile is created really just by the nonlinear process that we use from the laser, which then creates this pulse. It's about a picosecond long. So I like that it's a picosecond because inverse of a picosecond is a terahertz. So it has this Fourier content in it that is useful for us. So there are reasons, I actually didn't prepare any data to show there, where we have gone and taken this and run it through a filter. So it's a short pulse, which means it has lots of frequencies in it. And that is both good for us sometimes, because we can get a lot of frequencies all the time, but it also makes it challenging to get detailed spectroscopic information about systems. And so what we have done on some other occasions is run this through a filter, and then we get much longer. You might get, instead of like one oscillation, you might get 30, and now it's narrowly peaked in some frequency range, and we can use that for other reasons. So what I want to also talk about, this kind of gets into the kind of the technical details of how the experiments are done. This guy is about a picosecond long, and so its frequencies kind of more or less stop at around 1 terahertz. But for some of the experiments I'll show you at the end, we actually needed higher frequencies. And so instead of using a crystal that was this lithium niobate, which made that peak is kind of characteristic for it, we're actually taking a laser, doubling it, and then using it to ionize air, using the air itself as an emitting media, which allows us to get frequency components to very high frequencies, which is then useful for us. So if we had a knob and we could tune things, and that would be great. Life is, the experiments are complicated enough. We have some limited tuning, and we're using that to some extent. One thing I should say is that we're really at the early stages of my group, and other groups are really very much at the early stages of this. And so I don't think we really know where we're going with this yet.
How intense the terahertz pulses should be? You were speaking about like the EV pulses put a lot of energy into the system,
yeah.
But here does the intensity of the terahertz matter, and how do you tune it for your experiments?
Yeah, so that's an important point. So indeed, we want to have a gentle probe. So I think that and this is like the first correction to gentleness, right? So we're pushing things a little bit harder, but in a way that we hope is controlled. So it really, how strong the pulses can be very much depends on what's the material that you're probing. So superconductors are very delicate for intense terahertz pulses. And so we've done, again, I'm not showing much of that data here, but we've done experiments where we're looking at for collective modes in superconductors. So the amplitude mode, which is maps to the Higgs mode of the fundamental vacuum. So in those experiments, you really stop to be able to learn anything about the low energy, kind of the elementary excitations of the ground state when you get much above to about 10 kilovolts per centimeter, which is not a large field at all. So they're very, very sensitive. So with 30 or 40 kilovolts in a conventional superconductor, you just kill the superconductivity altogether. So that's clearly not the kind of thing that, you might want to do that. I don't know why you would want to do that, but some people are interested in that. But that's not been my focus. In the experiments I'll show you on metals, so metals have more low energy degrees of freedom, they can absorb more energy. And so you also need to use a large enough signal that you kind of push the regime where you have you push it nonlinear enough that you can start to see some response. And so we will find there that the best experiments that we're doing are something on the order of about 20 or 30 kilovolts per centimeter. And if we go much above that, we start to see deviations from the response scaling with the third power of the field. So that's really the key, is we want to be looking at that Chi3 susceptibility. If you keep going, you can start to see higher order effects, Chi5, Chi7, but then pretty soon they all start to kind of get on top of each other, and you kind of get into a regime where you have non-perturbative effects. And that's a very complicated thing that I don't think, at this point, we have no business thinking about in systems like these. Final point on that is that, again, it depends on what you're interested in. So one of the things I'll show you is the use of this on looking at magnets. So in magnets, let's say some antiferromagnet system, which has some magnon modes, antiferromagnon modes, there the coupling of the light is through a magnetic dipole. And that's very weak, much weaker than electric dipole coupling. And so that will roughly be about 2 powers the fine structure constant weaker than electric dipole coupling. So that's a factor of 10 to the 4th. And then you have this 10 to the 4th, but it's also, you're coupling with 3 powers of the magnetic dipole. So it's a 10 to the 12th times weaker. So there we really have to drive the system as hard as we can to be able to see anything having to do with magnetism. So there's no straightforward answer, but you have to be careful, and it very much depends upon the material you're investigating.
Yeah, just another question. Are these 2 terahertz pulses with same intensity, or one of them should be really acting as a probe and another one like as a drive?
Right. So in the literature, you will hear people use like a pump probe geometry or a pump probe scheme, where very often the probe is much weaker. We generally haven't been doing that in what we're doing, but it could be done like that. And for some things, it's useful. Again, let me not get into all the kind of the technical details. As far as what we're doing, it's fine that they're the same.
Can I ask a question? Since you mentioned this, you see in DC experiments, the electric field is in the range of, let's say, millivolt per centimeter. And the drift velocity is very small compared to Fermi velocity. I wonder if you are putting something like 100 kilovolt per centimeter, which is the pulse I'm seeing, and the numbers you get, the drift velocity can become supersonic in the sense that, so the electrons, your drift velocity, at least for that picosecond, will be larger than the velocity of sound, still below the Fermi velocity. Yeah. So you are still in your degeneracy. Have you ever seen anything?
I don't think so. So we wouldn't use 100 kilovolts per centimeter on a metal.
I'm seeing,
yeah, I mean, on this plot, it's, this is just some, not the real data that I'll show you is not measured.
So maybe I can ask another question about this. Why, this is a pulse, why there are blips afterward, and why the 2 blips are not exactly the same?
So they come out of different crystals. So they're 2 different crystals, and this is an imperfect process. So the laser comes in and is focused onto a particular crystal. That crystal emits this radiation. And so, we do our best to make them as close to each other as possible, but our best is not perfect. So it's just some detail, but it's not also it's not a very important detail. Indeed, hundreds of kilovolts per centimeter, that's true on this data. But when I show you data on the cuprates, it'll be 10 kilovolts per centimeter, which you still might say is a lot. And I would agree with you from the argument that you just give. On the other hand, if I look to see how that scales with the applied field, it seems for those fields we're solidly in the Chi3 regime. Which is not to say...
but has anybody been interested in looking at this supersonic regime, which is by itself interesting?
Supersonic, that's a good question. So there's some work which has been done where people are looking at narrow gap semiconductors, but they're mostly thinking about how when they excite to very high momenta, how they can start to get away where the band isn't parabolic anymore in narrow gap semiconductors. So they want to look to see the narrow gap semiconductor, if you go to high enough momentum, it'll be linear, and then we'll start to curve over. So there's discussion about clock oscillations, and whether you can see those in these systems when you drive them very strong. I don't have anything. It's an interesting point. I don't have anything to say about it, but let's think about it, because I'm not sure. I think that the regime that we and others who are doing experiments like this are in are solidly in this kind of perturbative regime, but I don't have a better answer for you.
Sorry, can I ask a stupid question? I thought I remembered that the sound velocity in, say, a 3D Fermi liquid was not sensibly different from the Fermi velocity.
No, it's in a regular metal. You see, these are numbers. The sound velocity in any solid you have is set by Debye temperature, which is about a few kilometers per second. The Fermi velocity of copper is hundreds of kilometers. So there is still two
When you
doses
said
of
sound velocity, you meant that of phonons.
because these are in helium-3 the two numbers are very
Not
similar.
plasma phones.
Okay, good.
So
That was my
He means real
confusion.
phonon, real sound.
This was my confusion.
Okay, so what can we learn with this technique? Let's think about that a little bit. I'm a little bit running out. I'm going to run out of time here. So okay, I'll get into it. Yeah, let me just I'll just kind of rush through this. The point of this slide is, one, it will impress upon you that things are complicated, and two, that we have some way of understanding that complication. So the first thing I would say is this, right? So that's a kind of the classical electric field. This is this protocol I talked to you earlier about. Like, imagine the polarization we make with two pulses at the same time, minus the polarization of one pulse by itself is the other pulse by itself. We can take this, and if we're driving a system with a chi3 susceptibility, it has that form, and I can take this electric field and I can plop it into here and multiply it out, and I got a big mess. It's not quite as bad as it looks because everything is coming in complex conjugate pairs. So it's only half as complicated as it looks. The other thing, if you look at it and you start to look at the arguments here and the exponentials, you'll see that there's some kind of systematics to it. So there's this guy here, which we'll call the third harmonic response, which looks like 2 omega j plus omega k, right? So that would oscillate at, so that's the third harmonic response. There's this response here, right, which looks like omega j minus omega j plus omega k, and that comes from a form of E star times E. And E star is an intensity. So this looks like an intensity, right? Like I pump the system, you can imagine absorbing a photon, and then I come in some later time with another photon and probe the system. So I'm kind of like, we like to use the language of nonlinear response, but it's kind of like a non-equilibrium thing, where we pump the system, but just a little bit, and then we're looking to see how it responds in this slightly pumped state, pumped by terahertz. That's the response that is going to be mostly useful for us when we look at metals. This guy here, looks like E star, and let me not tell you why it is, but I will just tell you that this is what we call the rephasing response. And if you're familiar with the idea of spin echo, like in magnetic resonance, nuclear magnetic resonance, we don't usually use the language of perturbative expansion for understanding magnetic resonance. Usually you think of like Hahn echo, pi over 2 pulse, pi pulse is this kind of language. But in a perturbative scheme, that's the Hahn echo right there. So that's also useful for us. Okay, so this is an example of that. So those different, again, it looks like a big mess, but all those different frequency contributions, one of the reasons we plot this as 2D terahertz spectroscopy is those different frequency contributions are different places in the 2D response, right? And we're going to understand that by using what we call this frequency vector scheme. So if I have omega j as one of the drive fields and omega k as the pump field, then this is for a particular ferromagnet here, antiferromagnet, excuse me, yttrium ferrite. There's two different modes. That's what the time domain data looks like. And there are these different peaks here in different places that correspond to different processes. And this is one of the reasons why we're going to go through all of this trouble, is because in linear response, if I have a ground state and excited state, and I want to go from the ground state to excited state, there's essentially just one way to excite. In nonlinear response, there are many possible paths. The chemists would call this Louisville pathways that I take from the ground state to the excited state. So I can excite the state, I can excite it again, I can de-excite it. I can excite it, de-excite it, excite it again, right? And all of this carries different kinds of information about the nature of interactions in the system, okay? And so this guy right here, that's the rephasing response. So that's the echo signal. That's the pump probe signal. This is a system which has a small inversion symmetry breaking. So you get a second harmonic generation up there. That's called the 2Q signal. And that corresponds to exciting 2 magnons and then de-exciting it. So the 2 magnon state by itself doesn't radiate. And then we de-excite it to a 1 magnon state. So it's 3 photons. 1 photon excites, another photon excites again, and then another photon comes on, de-excites it. And then by spontaneous emission, there's another photon that comes out, which is what we measure, and it carries information about the system when 2 magnons have been excited, right? So potentially information about the interactions between 2 magnons, yeah.
So I mean, in the simplest interpretation of the data, you can see where peaks are starting to appear, and that can give you direct insight into symmetries, et cetera, et cetera. So is there also information hidden in intensities, or is that more complicated even?
So the intensities, yes, but I would say that we're mostly what we've been using so far is widths of features, right? So that's not very obvious in this plot here because it's just, this is actually the magnitude of the signal. But in some data that what I'll show you about, we're going to be thinking about how do these things decay as a function of time, or in the Fourier transforms, the widths of features. And that tells us something about the particular process here. If we need a little bit of insight, and I didn't prepare slides on that. We've done work on what we call an electronic glass system, which is an ensemble of two-level systems. So in two-level systems, we understand what all the possible states are. Now we have interacting two-level systems. And so the language of magnetic resonance is very useful for us, like T1 times, T2 times, all of these kinds of things can be just exported directly into understanding data like this. And so we can learn about T1 and T2 separately. So the widths are important for us. In a metal, there's no echoes. And so this T1, the pump probe signal, is going to be the dominant response. And that's something that is proportional, as I will tell you about energy relaxation.
And final question, the streaks that you see in between the main peaks that you highlight, are those from doing Fourier transforms, or are they?
The streaks are coming because what is plotted here is the magnitude of the signal. So imagine I had, like, just think about linear response for a moment. This is maybe only a few people will understand what I'm talking about here. But if I have a Lorentz oscillator and there's a delta function, it's broadening on each side by 1 over omega minus omega c. So if I plot the magnitude of the conductivity, I won't see a delta function. I'll see a 1 over omega cusp around that frequency. And so that's essentially what you see here. You see these long tails. Okay. Good, right. So there's all of these different things, and we can locate them in different ways by this frequency vector seen. This is for magnets where there's well-defined modes. The pump probe response, that guy right there, is what's mostly useful for metals. And this is a system which breaks inversion symmetry, and there's a second Armitage generation. Let me, in the interest of time, just skip through all of this stuff here and get to some examples. And here. So when I first started thinking about this as a possible probe of interesting materials, this was my initial idea, which is something we're still working on yet. But I'll tell you about this, and then I'll tell you about the stuff we're doing on metals, which is really the correlated metals, which is really the main topic of this conference. So, and that's thinking about spin systems with fractionalization. So many people are interested in the idea of a quantum spin liquid. And so the idea of a quantum spin liquid is that, imagine I have a bunch of spins in a lattice with essentially antiferromagnetic-like interactions. And that lattice has a triangular motif. And so these two spins want to point in the opposite directions, but that third one has to choose which one it favors, and in certain circumstances it can't. Now, one of the things that can happen is that you can favor this kind of tendency towards local spin anti-alignment can be found through the formation of singlets. So where we're representing that by this triangular lattice where these kind of oval lozenge-shaped things, which represent a singlet state. So again, the tendency for anti-alignment is coming in because this system of the lozenges are a superposition of spin up, spin down, with spin down, spin up with minus sign. And then you can imagine all the different ways that you could tile the triangular lattice. But the expectation is the true ground state is the massive quantum superposition of all the possible classical tilings of the lozenge. Okay. Now, one of the difficulties, and so that would be kind of a neat thing to have this massive quantum superposition, but one of the difficulties is trying to understand what it would look like in the excitation spectrum. And the problem is the following. So this is a cartoon of what would happen. Let me pick one of those classical ground states. If a neutron or a photon comes in and takes that spin 0 object and splits it up and turns it into spin 1, these two guys can move separately. And so I deposit energy and momentum and perhaps spin in the lattice, and it's carried off in two separate particles, which means that the line shapes are really broad. They're very difficult to see anything happening. As a spectroscope, somebody who's made his career in spectroscopy, it's a very unappealing situation because you kind of like declare victory because you say that the spectrum is broad and boring. As a spectroscopist, we want to see sharp peaks. And so how can we possibly do that? So that's an example of data which is very interesting. On the other hand, doesn't show a whole lot of structure. This is a material ytterbium manganese gallium 04, which is a triangular lattice, which some people have thought is a quantum spin liquid. Others think because there's large amounts of disorder in the system that the spectral features are just completely washed out. So the exotic explanation of the spectrum is that this kind of area in here, this is the spectrum, you don't see any sharp peaks. If there were magnons in here, you would see sharp dispersive modes, but that this is evidence for some kind of spin-on continuum from a spin-on Fermi surface. That's what was.
Peter, what kind of data am I looking at?
That's neutron scattering.
Oh, so
Yeah, I'm sorry if that wasn't clear. Yes.
And the lower panels are photo emission?
It's all neutron scattering. All neutron scattering, yeah. So the point is that there's nothing interesting to see. And the implicit point has been, isn't it interesting how little interesting there is? We want to see sharp peaks. And so the proposal that I had some years ago was that you could use two-dimensional coherent spectroscopy to see sharp peaks in a spectrum which was broad. And so I gave you that example, extended example about the pendula, right? These coupled pendula where you could imagine maybe many of them altogether. So what we did in this is we calculated for the simplest possible model, which has fractionalization. The simplest possible model for fractionalization is just a ferromagnetic chain where an photon or neutron comes in and flips a spin, but the elementary excitations are essentially these domain walls here. And so energy and momentum is taken away by two particles, which give you a very broad line shape. And that's the calculation of it there. So that's the linear susceptibility, the imaginary part there, that kind of curved shape, right, as a function of frequency. This is an integrable model, and so in principle, all the excitations are eigenstates, and so they're all infinitely long-lived, but you can't see that because, again, the spectrum is just this blob of all of these things. But in the nonlinear response, you can see it right here. So this is a calculation of the nonlinear response, and that sharp streak there is like a streak, it's like a sheet of delta functions. And by taking a cut in the anti-diagonal direction here, you can get out its width, which there's some numerical errors here, and so it's not infinitely narrow, but it would be on the in the thermodynamic limit. Now, what you can do is, we went ahead then and just by hand put in decays into this model. And you can see when you go in the linear response from here to there, there's a little bit of broadening on the edge, but you would never believe me if I wanted to make some story out of that I could tell you how much broadening there is. But in the nonlinear response, that sheet of delta functions turns into this blob of which the antidiagonal width gives me the inverse lifetime. This here is a calculation which was done where we made all the couplings in the model random. So that's still an integrable model. The excitations are still energy eigenstates. You can see that, well, disorder broadens things. You go from here to there, they get a little bit broader on the edges. But you would never tell the difference between broadening from disorder and broadening from lifetime effects. But they're very different in the nonlinear response. Again, the sheet of delta functions. So this is an experiment we want to do. We're still working on it. It's hard because, as I mentioned earlier, magnetic dipole interactions with light are weak. I'm hopeful and confident it's going to work out. But let me tell you in the last, I'll go about 5 minutes over, the last bit what we're doing with this and have done in interacting metals. So this you've already seen. This is the linear Planckian temperature dependence of the resistivity. And we'd like to understand this relaxation rate, which goes linear in temperature. Now, one of the things about this is that I call this the current relaxation rate. And it is literally that, right? If the line shape is Lorentzian, that's the definition that comes from conductivity. If a Fermi surface is sufficiently isotropic, this is analogous to the momentum. This corresponds to the momentum relaxation rate. And so let me tell you something you know, but maybe in an unfamiliar way, and then presumably something that you don't know. So we imagine a kind of a simple Fermi surface, and we can imagine doing an optical conductivity experiment, but in the time domain. And so that's that, right? We take a Fermi surface, we shift it sideways, and then we could let it decay, and it comes back to the origin. That's a state of finite momentum. And so if that's going to decay, the electronic system has to lose momentum. The only scatterings which allow this thing to return back to zero momentum are scatterings which remove momentum from the electronic system, right? And so what does that in conventional electron theory? Electrons coupling to impurities, Umklapp scattering, electron Umklapp scattering, electrons coupling to phonons, right? Those are our choices in conventional theory, right? Simple kind of Ashcroft and Merman physics. Now, let me tell you something that it's decaying, right? And so there's a certain rate that's associated with that, right? It's the current relaxation rate, but it's really also the momentum relaxation rate if a system has sufficient isotropy. Okay. So now imagine I come in and do what I've been talking about, and that is using more than one pulse. And so in the first case that I just gave you a moment ago, the perturbation of the Fermi surface went like E cosine theta. It was a shift. Here, the perturbation is coming from this pump probe process. And so the perturbation is E squared, or really it's polarized light, so it's E cosine theta squared, right? Which you can take and split it up into two parts. We'll call it the S wave part, or in a cubic system, you would call it A1G, and then a D wave part here, right? And so to see how that works, right, you can drive it, decay. You see how it works. Imagine that, I kind of take a Fermi surface and I kind of do this with it, I jiggle it sideways, and that has the consequence of exciting here and exciting there, but it doesn't do anything there and there. But I can understand this then as a superposition of a kind of a uniform excitation all the way around, with an excitation which is like exciting here, exciting there, but de-exciting there and there. So if it was an isotropic system, I could call this the S wave and the D wave part, or here we'll call it the A1G and the B1G part, because we're mostly going to be thinking about crystals with C4 symmetry. Right, so this is something that I can do in nonlinear optics now. It turns out this is actually really easy for us to measure. And the decay of that is essentially the rate that energy leaves the electronic system. Right, so it is not a state of finite momentum, right, because it's excited everywhere around, but it's excited everywhere, and it can only decay by the rate that the electronic system loses energy. So electron-electron interactions of any kind don't matter because they just change the distribution function. Electrons scattering off of conventional impurities don't matter because that's just elastic scattering. The only thing that takes energy away from the electrons in the conventional case is electrons coupling, at low energies, is electrons coupling to acoustic phonons. Okay. This is different. And I'll show you some data. First time that data has gone live, but that data is, we can now measure this as well, and that's particularly interesting. So it couples to basically all kinds of scattering in the system, but in a way that's different than the P wave part, or the E wave, the E1U, or this one that I showed you could get out from linear response. Let's go to, okay, one more thing here, and then I told you I would go 5 minutes late. What do we know, for instance, about energy relaxation? So I want to talk about the part which is uniform around the Fermi surface. Its decay has to do with the rate that the system loses energy. And so let's take a simple case of electrons coupling to acoustic phonons. I mean, for momentum relaxation, we know that. That's kind of the conventional scheme, is that at low temperatures, it's T to the 5th or T to the 3rd, depending upon details, but some kind of power law. And then there's a region where things go linear in temperature, and that's typically called the elastic phonon regime. In this regime up here, electrons have more energy than the Debye temperature, and so scatterings are essentially elastic in nature. Now, the energy relaxation, this was first worked out by Phil Allen in 1987, at low energies has a T to the 3rd dependence predicted, and then there's a peak, and then goes like 1 over temperature in this elastic phonon regime. Why is that? Well, that's because if you go to high temperatures, the phonons become very inefficient in taking away energy from the electronic system. The electronic system has on average energy T above the Fermi energy, but they can only, every scattering event can only take away is the maximum of the Debye frequency. And in fact, a lot of the scatterings are putting Debye energy into the system, right? So it becomes very inefficient. So this is something we want to look at, and let me just say, because I'm running out of time, that this is something we've measured on lanthanum strontium copper oxide, and that's what data looks like. Again, this is going a little bit fast at the end here, but this is just kind of my own stuff at the end here. This is lots of different samples, right, which are really spanning. This is all done by my student Will Young, spanning a huge doping range. And these decays here, this is the newest data, is the rate that, again, this uniform part of the Fermi surface, the rate that this uniform part of excitation on the Fermi surface is decaying, and that's sensitive to the rate that energy leaves the electronic system. Okay, these are some fits to the data. Let me just show you maybe this here, because that kind of makes the point. This is a plot for one of those systems. In blue is this momentum relaxation rate here. So that is this kind of famous linear in T temperature dependence. with a coefficient very close to, in this case, it's very close to 2. And red is the energy relaxation rate. And note that they're plotted on different scales. So the thing that I want you to take away from this is that energy relaxation is much, much, much slower than momentum relaxation. Most of the scatter, coming back to what I said about scatterings, most of the scatterings that take away momentum from the system don't take away energy from it. So that's the point that you can take away from this. The other point that I will make is that this is linear in T over this whole range, and then this, of course, just continues on up to even higher temperatures. But in this whole range where this is linear in T, you don't see the 1/T dependence of the energy relaxation rate. So among other things, one of the things that this data does is rules out electron-phonon coupling as a source of the linear T resistivity of the cuprates, right? So I just don't see any way that that is possible with this data at all.
Peter?
Yeah.
This is very beautiful. This is one doping, and this is true for the whole doping?
It's true for all dopings, yeah.
Wow.
Yeah.
Mm.
Okay, final thing I will show you is that right, so we can do, this is, as I mentioned here, we can now with multiple pulses, if you will, distort the Fermi surface in different ways. And so conventional linear response measures this, right, if you will. I showed you a time domain version of this, but now this is like a frequency domain version of it. We take the Fermi surface and we're rocking it back and forth in this fashion. That's what, in this state, when I shift it, is a state of finite momentum. And so its decay measures the rate that momentum is pulled out of the electron system. This guy here, it's a little bit unfortunate plot because it looks like the density is changing, but really what I mean is like the energy, it's some kind of locus of momentum occupied states is expanding. These are states of finite energy here. There's this kind of breathing mode, if you will, of energy on the Fermi surface. But then there's this guy here, which is this, we're going to call B1G, which is this oscillation of the Fermi surface. In the old Russian literature, this would be referred to as a Pomeranchuk mode. And we can measure this as well. And that's, in the interest of time, let me not show you all of these kind of cool animations that Will's made. And that right there, right? So this is harder for us to measure. This was a incredible tour de force experiment for Will to measure. But what this is a plot of is the relaxation rate versus temperature for the B1G relaxation rate, which we get by doing multiple pulse experiments and looking at the symmetric and anti-symmetric combinations of the nonlinear response that comes out. And so this is the relaxation rate of this B1G deformation that if you were thinking about hydrodynamics, B1G is proportional to viscosity in the system, right? So it is a relaxation rate which is different from that of the E1U, which is the transport relaxation rate, and has a kind of understanding and kind of old school Fermi liquid theory, and that there's a kind of a numerology about all these different possible excitations of the Fermi surface and how the coefficient of their T-squared scattering. So this coefficient here is about 2, and it's the same coefficient that we find for the E1U rate in the case for the linear optical conductivity. And so, the takeaway message from this is that the E1U and the B1G are the same. And, whether this points or not to some kind of interesting universality in the dissipation processes and how fast they're allowed for this kind of strange metal physics is, something that, I'd like to have more conversations about. So I'll stop there. We're in a few minutes over. Anyway, yeah.
Any quick questions? 2 quick questions.
Great talk. I wanted to ask for the spin liquid part of that you didn't elaborate on. In principle, one way to couple, there are some materials in which you could couple to spin fluctuations through magnetoelastic coupling. And that would make essentially, would create some dipoles to which you could couple. Is good magnetoelastic coupling?
Electric dipoles, you mean?
Yeah. Would that coupling alter the line shape that you expect in the nonlinear spectrum?
So I don't know. To kind of Matteo's question is saying, basically reframing it, saying that these spins are not existing. Of course, we can write down a purely spin model, but they're existing in a lattice, and those spins are on ions that can move. And so generically, you expect there to be couplings between the electric dipole degrees of freedom of the lattice, for instance, and the spin degrees of freedom, which then should be essentially picked up by even the fractionalized spin degrees of freedom. And so my answer is, I don't know. What we're trying to do now is understand some of these magnetoelastic couplings for much simpler systems, because what we would like to know is, even for a magnon system, does it alter the line shapes at all? And so that is something that for, say, for some multiferroic systems, that those magnetoelastic couplings are already well known. And so we're working with some theorists to kind of try to work this out to see if we can understand it for magnons. And if we can understand for magnons, maybe we can then export it to looking at on spin liquids. It may be that magnetoelastic coupling is actually, it's not a bug, but a feature, because it improved, it kind of boosts up the scale of the coupling to light. And, I just don't know if it distorts the line shapes or not. My suspicion is no, but I don't.
Peter, can you show again your data on two plates?
This data?
No,
further back.
the raw data. Yeah, here. It's very beautiful, but and as far as I see, you clearly see an evolution from 9% to 29%. My question is, you are aware of, for example, the work done by Nigel Hussey about DC transport, that if you scan the same thing, you have T-linear resistivity, but this prefactor, of course, it is not alone. There is also a T-square, which becomes unique only when you get rid of superconductivity. Mm-hmm. And if I look at your data, the 9% and 29% are not the same. So my question is, first, just the bottom line, if this ratio of 26 between energy relaxation and momentum relaxation, it cannot be there from 9% to 29%.
No, it has some doping dependence, but I didn't show you. No, okay. So that's I would say that's a rough scale, but in all cases, it's much bigger.
So do you see when you are 29% T-linear plus T-square in either momentum or energy? And
we see something like this in the momentum relaxation.
As you would expect.
But in the energy relaxation, we haven't really thought much about what's the right way of understanding the particular functional dependencies on temperature.
Because at 35%, which is a Fermi liquid with an unusually large T-square, but it is T-square down to 0, and there is no T-linear. So maybe this is where you may start. At 29%, normally you should be very close to that, but you have not get rid of the T-linear part.
Yeah, we're thinking about it.
Thank you.
Okay, let's thank Peter again.